Hello, I'm going to start to tell you about the chemistry of the actinides. This is the second period of the F block, and ultimately you will see that there are some very significant differences between these elements and the first row of the F block, the lanthanides. But before we get into reactivity and the chemistry of the actinides, I need to talk about a physical property that dominates how we deal with these elements. So our periodic table starts with hydrogen, with a single proton at its nucleus, and continues with Z increasing 1 unit at a time. Where does it end? As we add protons and neutrons together in a nucleus, these particles are held together by the strong nuclear force. This is a very strong attractive force. However, the positively charged protons will also experience an electrostatic repulsive force. As we increase the number of protons, we increase the significance of this repulsive interaction. At some point, the electrostatic force is sufficient to destabilize the nucleus, which can then undergo a nuclear reaction, or a transmutation, or if you like, radioactive decay. Let's look at the elements where there are no known stable isotopes. With a couple of exceptions, number 43, technetium, and number 61, promethium, all of the unstable elements occur at the end of the periodic table. When I started studying chemistry, bismuth was considered to be the last known stable element. It turns out that we now know that this is not true. Actually, all isotopes of bismuth are unstable. It's just that the one that we thought was stable actually decays very, very slowly. So now, as far as we know, number 82, lead, is the last stable element. But clearly this is not the last element. Both thorium and uranium were known to Mendeleev and were included in his original table. Later we had Marie Curie and others filling in the gaps here. And so up until about 1944, the table stopped at number 92, uranium. With the Second World War and the Manhattan Project, we started to synthesize and create new elements, and we've been doing that ever since. At the moment, we've extended the periodic table all the way up to 118, oganesson. So the thing is, there is no definite end. There is lead, the last stable element. People often talk about uranium as the last naturally occurring element, but in fact we can find minute quantities of neptunium and plutonium in uranium ores. And of course there are natural astrophysical processes such as supernova and the collisions of neutron stars which would produce very many heavy and super heavy elements, albeit that most of these would have a relatively brief existence. From a chemical perspective, there is a practical end. As these elements become more and more unstable, and more difficult to produce, and more difficult to study, there is a significant cut-off in our chemical knowledge, somewhere towards the end of the actinide series. Each different isotope of an element is defined by a number of protons and a number of neutrons. Clearly, the stability of a particular nucleus depends upon these two things. So let's start by looking at the stability of one element as a discrete function of the number of neutrons present in the nucleus. Now, it's convenient to measure stability of a nucleus in terms of a half-life. The half-life is the time taken for half of a particular amount of a particular isotope to decay. The longer the half-life, the more stable the nucleus. If an atom is indefinitely stable, the half-life will be infinite. Of course, it becomes more and more difficult to measure half-lives of isotopes with very, very large values, simply because we have so few decay events to observe. So let's look at a familiar element from near the beginning of the periodic table. Let's take carbon and plot half-life versus atomic mass. There's a slight issue here. As far as we can tell, both carbon-12 and carbon-13 are indefinitely stable, or at least have a half-life that is much, much longer than the current age of the universe. So I need to truncate this plot. So in our linear plot, that is all we can see. But if we look at the same data on a semi-log plot, that will stretch out the relatively small values so we can visually compare them better. Again, I've truncated the graph to the age of the universe, And now we can see that the next most stable isotope is carbon-14, with a half-life of 5,730 years. Actually, this is a hugely significant isotope. Short-lived from a geological perspective, long-lived compared to human history. It is only generated in the atmosphere, and so is present in atmospheric carbon dioxide in small but relatively fixed quantities. The amount of carbon-14 left in some formerly organic, meaning living material, can give us an accurate date for when that thing was living. Back to isotopes of carbon. Well, that's about it here. These other isotopes are all relatively short-lived. Many here live less than 1 second. Okay, let's have a look at an actinide. Let's take thorium. All isotopes of thorium are radioactive. Each has a characteristic half-life. But one isotope, thorium-232, has a large half-life, much longer than the age of the solar system, although much shorter than the age of the universe. Again, if we replot the same data on a semi-log plot, that stretches the lower values. First of all, these variations are not smooth. They do not decrease uniformly on either side of the most stable isotope. Notice that from 230 upwards there is a very pronounced up-down effect. Next to a relatively stable isotope is a relatively unstable one, and vice versa. Thorium is atomic number Z equals 90, an even number. And it is the isotopes with an even number of neutrons that are more stable, while isotopes with an odd number of neutrons are less stable. This odd-even effect is related to the Odo-Hawkins rule. Okay, so for each element we can vary the number of neutrons, and so compare different isotopes. The other thing we should look at is varying the atomic number, the number of protons. This is a plot on a semi-log scale of the most stable isotopes from number 83, that's bismuth, to 103, that's lawrencium. What we can see is that from the very stable element bismuth, the stability drops, like a stone, to polonium, whose most stable isotope is polonium-209, with a half-life of just 125 years. Then we have astatine, radon and francium, elements that can only live for between minutes and days. But after that we increase the stability. Radium and actinium live for tens or hundreds of years. Then we come to a maximum at thorium and uranium, elements whose half-life is much larger than the age of the solar system. It means that for these elements, thorium and uranium, they were present at the very beginning of the formation of our planet, and they are mostly still here. We call these elements primordial elements. They are as old as the Earth itself. By contrast, atoms of elements from polonium to actinium that were present at the beginning of the formation of the Earth have long since decayed. These are not primordial elements. Their presence on Earth, in small quantities, is due to more recent decays of elements like thorium and uranium. Beyond uranium, we have neptunium, plutonium and americium and curium, all having relatively long half-lives, thousands of years for their most stable isotopes. Berkelium and californium are in the thousands of years regime, and then moving on, einsteinium, fermium and mendelevium cross the year mark. The last two actinides are nobelium and lawrencium, which take us down to 4 hours for lawrencium-262. Between number 88 radium and californium, or mendelevium depending on your perspective, we have a region of significant stability, meaning these are potentially elements that we could work with. The other feature about this plot is that the elements with an even atomic number are generally more stable than those odd-numbered elements. Back to Odo-Hawkins again. So the last thing I want to look at here is all of that in one go. If we plot atomic number Z versus neutron number N, we have a grid where every single square represents a different nucleide. For each different nuclei we can plot the half-life. Here it is, colour-coded. There is a huge amount of data in this plot, and it really reveals how stability varies as a function of nuclear composition. There is a dark line of stable isotopes, It's approximately linear for the first 18 or so elements. These are elements whose stable isotopes have equal numbers of protons and neutrons. But as Z increases and the electrostatic repulsion becomes more significant, we find that nuclei with a higher proportion of electrically neutral neutrons become more stable. The line of stability is very narrow. Indeed, it is a fine line between stability and instability. We also see that most odd-numbered elements only have one stable isotope, while even-numbered elements may have several stable isotopes. But these tend to require an even number of neutrons. I need to tell you there's quite a lot of unknown here. It's very hard to make extremely neutron-rich nuclei, so we are missing data on the side of this valley of stability. In addition, it becomes harder and harder to make atoms of the highest atomic number, the largest values of Z. All in all, this limits the range of our observational data. There remains a possibility that we might find some as yet undiscovered heavier nuclei that have some significant stability. And if we can, what happens next to the electronic structure of these atoms? When we get to the hypothetical element 121, does it sit underneath actinium at the start of the third period of the F block? Or do we start to occupy the 5g orbitals and begin a whole new block, a G block of elements?